Hello, I wanted to start talking about section 410, 1 and 2. Okay, these sections concern linear independence and linear combinations here. Okay, we have to look at some definitions first to get our understanding down here. Okay, first thing just a quick definition here. I usually underline my definitions. A linear combination of vectors is a sum of scalar multiples of the vectors. Okay? So that's what a linear combination of vectors is. It's just a sum of scalar multiples of the vectors. So let's take a concrete example. This is really easy concept. Okay? So for an example of a linear combination here, suppose I had u equal 1, negative 2, and v being 3, 4. Okay, so I'll write my vectors as column vectors. Okay, can you give me a linear combination of those two? Well, there's infinitely many ways to do it. I could do this. 2u plus v, that's a linear combination, so that would be what? If I go 2 times this vector, I would get that, 2, negative 4. And if I was to add v to it, then I would get what? The vector 5, 0. Okay? So we could say the vector 5, 0 is what? A linear combination of these two. And in fact, it's what? 2 times u plus v. Okay? Now, there's infinitely many different linear combinations of u and v, right? This isn't the only linear combination. So let's talk about the set of all linear combinations of vectors, of a set of vectors. It's something called the span. The span of a set of vectors is the set of all linear combinations from the set of vectors. Okay? So if I've got v, my set, being u1, u2, down to uk, and let's say those all belong to n vectors. They're all real n vectors. By the way, this could be what? This could be the complex numbers, by the way. We shall do that later. Okay? Then what we're calling the span of v is all vectors of this type, where I've got what? Some scalar multiple of u1 plus some scalar multiple of u2, all the way down plus some scalar multiple of u sub k. Okay? All right, now we're considering all such vectors, okay? So we're imagining the a sub i's here, the scalars running throughout, ranging all the way throughout the real numbers. Again, that could be the complex numbers here, okay? So you understand what the span means, okay? So it's all linear combinations. So we would consider what the span of these two vectors here would be all vectors of maybe this type. Instead of using subscripts here, okay, it would be the set of all, okay? This would be the span of my v in this case. If I threw those together in a set and called it v, the span of v would be the set of all vectors here, such that what? A and b is real, okay? Again, could be complex here, okay? So all of them like this. Now, it might be a challenge for you here. Could you actually tell me what the span of these two vectors actually is? Could you characterize the span of these two? Okay, that's what we would call an EFY, exercise for you. Okay, find the span of these two. Well, there's some questions like that in the book for the homework. Okay, all right, so you understand the idea of span of vectors, not difficult. Okay, something that's slightly more abstract, but it's not too bad either, is the idea of linear independence, okay? So I'm going to have a set of vectors like v up here. I've got a set. It's always going to be a finite set in this class too. A finite set of vectors v is linearly independent if every vector in the span of v has a unique representation as a linear combination of the vectors of v. Otherwise, the set is said to be linearly dependent. Okay? So we're saying every vector in the span of v has what? A unique expression as a linear combination of the elements of v. Here's another characterization which I think your book actually uses as the original definition, okay? But this is going to be equivalent to this. Here's an equivalent way of writing it, okay? So I say there are different ways of expressing the idea of linear independence. So this is my V here, my set of vectors, okay? I've got K of them. Here's one way of expressing this. The zero vector can be expressed as a linear combination of the vectors of V if and only if, what? All the scalars are zero, okay? So the only way to get the zero vector is what? For all the scalars to be zero. That's equivalent to what? This set of vectors being linearly independent, okay? All right? So we can show that these are actually mean the same thing. Let me throw in here just some examples here to get the idea of linear independence and linear dependence, right? Because don't forget, we have another definition here in here. It says, what is it if the vectors are not linearly independent? What do we say? They are linearly dependent, okay? Let's get the idea here of some of these, okay? Let's say I had a couple vectors like this. Let's say V was U, V, W, okay? And it so happened that W was 2U plus V, okay? It just so happened, okay? I could actually write them as vectors like I did up here, right? Maybe, okay? All right, something like this situation. That set V, could that set V possibly be linearly independent? And the answer is no. Well, by our first definition here, this is obviously not a linearly independent set because what? This vector is a linear combination of the other two, right? It's 2U plus 1V, okay? What's the other way of looking at it? It was saying the only way to get the zero vector using all these vectors from the set is if what? The scalars are all zero. Well, let's see, that's going to be false here. Suppose I had this, okay, and I had that being the zero vector. It's true if all the A's are zero, then I get the zero vector, right? Okay, but is that the only way it can happen? For linear independence, the only way that can happen is for all these to be zero. Okay, I'm going to show you that's not true, right? All right, watch. What if I have negative 2U minus V plus 1W? I'll just write that as W. Okay? Well, isn't that the zero vector? Okay? It is, in fact, because I've got negative 2U minus V. Well, W was actually this linear combination of these two. Now think about it. You get cancellation here and here, right? This is the zero vector. But wait, my A's here, what's the A1? A1 here is what? Negative 2. A2 here is negative 1. And A3 is 1. They're not all zeros, okay? They're not all zeros, okay? This is not linearly independent, okay? So not Li. What's another way of saying that then? Linearly dependent, okay? And you can see this situation's always going to happen whenever what? You've got at least one of these vectors as a linear combination of the others. Can you see that I could always play this little trick here and get the zero vector without having the A constants, the A scalars being zero? Okay, so I hope that makes that idea clear. It's hopefully pretty intuitive here. Okay, so this is a linearly dependent set. Okay, by the way, if I tossed one of this out like that, okay, well, you'd have to see what the vectors are before you could tell whether these are linearly independent, right? Okay, you couldn't know. I'd have to actually give you specific vectors for you to know at that point. Okay? Okay. Here's another way to think about this. let's put the emphasis on linear dependence, okay? Because we want your intuition about this stuff, okay? Let's talk about linear dependence. In essence, what I'm saying is a set of vectors is linearly dependent if one or more of the vectors in the set can be expressed as a linear combination of the others. A sort of succinct way of saying this, the set contains redundant vectors that can be dispensed with in the span. Okay? Like in this example here. If I was going to compute the span of V, remember that's the set of all linear combinations of U, V, and W. Okay? Would I really need W, for example? Well, no. You see, I would get exactly the same span if I just used U and V. What good is W doing me? Nothing. It's not doing me any good, at least with regard to the span, right? So this is a redundant vector. That's what we mean. So that's linear dependence, okay? All right. Well, with your readings in the book in this video, hopefully you'll get the idea pretty quickly. It's not real difficult. It's just a matter of getting used to the idea. Okay? Let's turn this over and talk about one last idea here. Invertible matrices and linear independence. You've got a theorem in the book, Theorem 4.74. Okay? Let's take a look at this and then get the idea. Suppose that A is an element of R to the what? N by N, or C to the N by N. What did that mean again? Oh yeah, okay, that's what? A real N by N matrix, or what? Complex N by N matrix. Okay, so I've got an N by N matrix, so it's a square matrix, and let's suppose it's invertible. Okay, so it's invertible. Another way of saying that would be what? Its determinant is not zero, right? Remember that? Okay, just throwing that in there. But suppose it is invertible, then the columns, and it turns out the rows as well, I'll let you think about that, then the columns are linearly independent and span R of n. Okay? The columns are linearly independent and span R of n. Let's go ahead and try to see why that holds there. Okay? Maybe I was thinking about a situation where you could see it really concretely by taking a particular example. Okay? Let's consider this thing here. Okay? Let's say I have this matrix here. 1, 1, 0, 1, 0, 1. Okay, 0, 1, 1. All right, so let's say that's my A. Okay? Are these columns linearly independent? Well, what would you do? You could do the following here. So let's just say this. Are the columns linearly independent? Okay. What would you do? What would be one way of doing this? Well, you could take the determinant. Okay. These numbers are nice and small, and it's only a 3 by 3, so I'll go ahead and compute this. And then we'll say, oops, that's a 0, 1, 1. Okay. Maybe expand across the first row, so I would have what? 1 times, okay, get rid of the first column in the first row. Okay, so I'm doing it starting right here. Okay, and we'd have what? 0, 1, 1, 1. Okay, remember, change sign. Now it's going to be minus. Okay, get rid of the first row and the second column, and we'd have what? 1, 1, 0, 1. And I'll ignore the last because what? I've got a 0 factor there. We don't need to worry about that. So that's 1 times, what do we get here? Negative 1, I think, minus 1 times 1, and we get what? Negative 2. That's not equal to 0, so A is invertible. A inverse exists, in other words. Okay, and by the theorem, the columns are linearly independent. Okay, so that's just an illustration of the theorem. Now let's go ahead and see why this is happening here. Okay, try to get an idea, and I'll even think of it this way, with these particular columns here. Okay, let's actually take these columns and write them as separate vectors. Let's say U is 1, 1, 0. V is the second column, that's 1, 0, 1. Okay. W is, what was it, 0, 1, 1. Okay. Are either one of these a linear combination of the other two? That's another way of thinking about it. Okay, let's consider these. Okay, now let's go back to one of our formulations, one of our definitions of linear independence here. Yeah, I'll call it A1. Let's go A1 plus A2. I used alpha there at first, sorry about it. Okay, A3, and let's say I'm going to set this to 0. Okay, in order to be linearly independent, what would have to be true? The only solution to this would be what? 0 for A1, 0 for A2, 0 for A3, right? Okay, now if you look at this though, you can't help but kind of notice, now I'm trying to show you why this theorem works here. You can't help but notice, wait a minute, I could write this as a matrix equation, right? I could write this way. Like that. Now, just consider here. Here's, oh wait, that's my A there, isn't it? Okay. Now suppose that A is invertible. Suppose that A is invertible. What does that mean then? That means A inverse exists. I could multiply on both sides by A inverse on the left multiples, right? Correct? Okay? And then you have the associative property, so A inverse A is the identity, 3 by 3 identity, which when multiplied on that gives that column vector. So we would conclude, if A inverse exists, then we would have what? A inverse multiplying on this side too. But wait a minute, what's on this side? What's that product there? That's going to be all zeros. Oh. So do you guys see, if A inverse exists, then there is going to be what? A unique solution here, right? Namely, A1 equals A2 equals A3 is 0. Thus, if A inverse exists, in other words, A is invertible, then it is indeed true that these are what? Linearly independent. Now, conversely, suppose that A inverse doesn't exist here, okay? A inverse doesn't exist. It's not invertible. Then what would happen? Well, you know that means that the rank of this matrix would be less than 3, right? That means what? You've got a row that's actually a multiple or a linear combination of other rows here. You would actually get down to a situation where you've got, now this is going to always be consistent because I've got zeros on this side. Think of it in terms of Gaussian elimination. You see, you would have a situation like this appearing in, I don't know what these numbers would be, and these would be zeros here. Okay. Where you could actually get what? You could actually get non-zero solutions to a situation like this. Okay? Non-zero solutions to the A1, A2, A3 in our original equation up here. Okay? So this is the essence of the idea why theorem 4.74 works. Okay? Now, so that means if you're looking at what? An n by n matrix, and you find out it's invertible, what does that mean? That means the columns are linearly independent. Considering, by the way, let's just throw this in, transposes, you could also say the rows are linearly independent. Okay? That only holds for square matrices, though, of course. There's no such idea of invertible non-square matrices. All right, just an introduction to these ideas. Hopefully it helps there. You can read some of the proofs in the book for greater details there. Okay?